Hello, everybody, and welcome back to another lecture in Geography 340 Climatology. I'm Dr. Zach Hilgendorf. Today, we're going to be talking about cloud formation and diving into the first of a number of different lectures on cloud formation, air masses, and frontal systems, and precipitation development as well. I apologize if there's some added noise in the background. My little one is between feedings and not thrilled, so excuse the extra noise. But let's go ahead and dive into it. So just a bit of a recap. Let's go ahead and talk about some of the moisture terms that we learned in the last lecture. These are going to be important concepts to think about as we're understanding how air parcels move about in the atmosphere and how that movement and temperature changes lead to the development and formation of clouds. So the first one, humidity, the water vapor content of air. Basically saying what is the average water vapor content of air, what are sources of humidity, what are sinks of humidity. These are topics that we talked about in our previous lectures. Humidity indices or measures include specific humidity, which is the mass of water vapor per unit mass of air. We usually measure that in grams per kilogram. Mixing ratio, the mass of water vapor per unit mass of dry air, again in grams per kilogram. We said that the specific humidity is 10 grams per kilogram. Our mixing ratio would be 10 grams per 90 or 0.99 kilograms, give us a mixing ratio of 10.10 kilograms or grams per kilogram, pardon me. Likewise, if our specific humidity was 20 grams per kilogram, mixing ratio, we'd say 20 grams divided by 0.98 grams or kilograms. That'd give us 20.41 grams per kilogram. And 30, we get 30.93. Moving into vapor pressure, the part of air pressure due to water vapor. Air pressure, force per unit area exerted by randomly moving gas molecules bouncing off a surface. We saw this figure previously. And the partial pressure of water vapor in millibars. Relative humidity is the ratio of actual water vapor content of air to what the water vapor content would be if that air parcel were fully saturated. Saturation. This is a really important concept, especially in this and the next lecture. So saturation or saturated air is the humidity state that exists when the rate of evaporation from and the rate of condensation onto a flat water surface is equal. So basically, if evaporation and condensation are equaled out, we have a saturated air parcel. Relative humidity, the ratio of actual and then moving into dew point, the temperature at which air, given its vapor pressure, would be saturated. So now we're going to move into the meat of today's lecture, cloud forming processes. So we're going to be starting off in this video looking at diabatic processes, and in the next it'll be adiabatic processes. But first, what are clouds? So it seems like a simple question, right? They're the white fluffy things that float above us. Basically, though, they're atmospheric particulates of water. Typical radius of that particulate matter equals 10 micrometers. It's comprised of liquid water droplets, solid ice crystals, and a combination of the liquid and solid. So you have particles floating about in the atmosphere. They form and act as a nuclei for cloud development and for those water droplets or ice crystals to form onto. And as they form and kind of aggregate amongst them, we have the development of clouds. So how do they form? condensation or deposition in the atmosphere. Think of our phase changes of water. What are the requirements for condensation in the atmosphere? Well, as I said, we need a condensation nuclei. These are hygroscopic aerosols, are a good option for that. Hygroscopic meaning that the water content or the molecules of water are bound incredibly tight to the nuclei point. If you recall back to 104 in our soils, we talked about hygroscopic soil moisture. Same kind of concept here. This hygroscopic force is one that is binding the water molecules tightly to whatever that nuclei point is. Typical radius is 0.1 micrometers. Saturated air, 100% relative humidity, more or less, is required for that condensation to occur. We see our plate example here. If this was our flat water surface, our vapor pressure here, 12.3 millibars. Our saturated vapor pressure, 12.3 millibars. And our temperature of our water and air, 10 degrees Celsius. So for a given water temperature, the evaporation rate from a curved surface is greater than the evaporation rate from a flat surface. Kind of here. So if we think of our flat surface, less than that of our curved surface here. For a given water temperature, the evaporation rate from an aqueous solution is less than the evaporation rate from pure water. Requirements for deposition within our atmosphere. Saturated air, so 100% relative humidity, more or less. Deposition again, or ice nuclei. See these beautiful snowflakes here. Or, for example, kaolinite crystals could be another option. And this form of deposition really becomes effective at about less than -4 degrees Celsius. So, requirements for condensation or deposition, we need that saturated air. That's what we're going to focus on first. So how does air become saturated? Well, the first option, first potential possibility, is you add water vapor to it. Here we can see fog or precipitation fog or frontal fog. This is fog that forms from rain evaporating as it falls through a layer of cold or cool air. You can mix cold air with moist, warm air. We see our example here. We've seen this graph in previous lectures. So here's our saturation vapor pressure versus temperature. Saturation vapor pressure is on the left axis, temperature on the bottom. So here, if we look at these 2 points, contrails are another one. See, contrails being a cloud-like streamer frequently observed behind aircraft flying in clear, cold, and humid air, caused by the addition to the atmosphere of water vapor from engine exhaust gases. There's our additional water vapor being added within a particular parcel of air. We've also got steam evaporation fog, or steam or evaporation fog, the same thing. Fog that has the appearance of steam that is produced by evaporation from a warm water surface into the cool air above. We have lake effect clouds. So here the general idea is as air flows over the relatively warm lakes, for example, Lake Superior, Lake Michigan in the winter times, the cold, dry air gathers heat and moisture from the surface. This warm, moist air rises rapidly, mixing with cold, dry air above. Some form these streamers of fog. You can kind of see those curved linear features for the most part coming off of Lake Superior from the kind of northwest towards the southeast. Some of these form streamers of fog rising from the surface, while others condense to form stratocumulus clouds in the upper half of this mixed layer. You can form or saturate air by cooling it to its dew point. How is air cooled to its dew point? Two primary methods: diabatic cooling and adiabatic cooling. One of those you should remember or may recall from Geography 104 in the Moisture in the Atmosphere lab, where we went up and over the mountain, right? Mount Doom is one of my favorite labs just because I'm a big Lord of the Rings nerd. We have these two different processes. So diabatic processes are basically any temperature change in air or of air that is not related to adiabatic vertical displacement. Adiabatic processes deal with changing temperature of a parcel of air due to the air rising or sinking adiabatically. Adiabatic processes assume that no heat, mass, or momentum pass across this air parcel boundary. Rates of adiabatic change occur differently depending on whether or not the parcel of air is saturated or unsaturated. So we're going to focus on adiabatic cooling and change in the next lecture. This one, we're going to be focusing on that diabatic process. So basically, the change of temperature in an air parcel not related to vertical displacement of that air parcel. So here we can see our first example, radiation fog. So this is the general term for kind of a broader group of fog types. So radiation fog results from radiation cooling of the ground and adjacent air, primarily during nighttime and early morning. You can see kind of rising off the surface here, based off of primarily in radiation fog, you typically may have light winds, little to no winds, a high pressure system. So you don't have clouds kind of capping the atmosphere and holding that heat in. And heat is able to move more freely into the atmosphere from the surface through that long wave radiation heating coming from Earth. So here you've got that radiation cooling occurring. Another one is called Thule fog. This is a special type of radiation fog that occurs each winter in the Central Valley of California. We can see it starting here in December 19th of this year. So what happens here is you have this combination of cool, moist layer of air coming from the Pacific close to the surface. You've got clear skies and light winds. And what you have is exceptionally thick fogs on many nights from late October through February. So if we look here, December 19th, there's San Francisco, watched primarily up by San Francisco. Here we can see December 20th, the entire Central Valley is getting basically flooded with fog. And there we can see it again in December 21st. So this is from December 19th to the 21st, just a 3-day period. You can see just how dense and thick that fog is going through the whole of the Central Valley. Next, we've got valley fog. So under stable nighttime conditions, long-wave radiation is emitted by the ground. This cools the ground, which causes a temperature inversion. In turn, moist air near the ground cools to its dew point. Once you reach that dew point, you have saturation. When you have saturation, you have cloud development. So here we can see valley fog development. We see this a lot of times in kind of the, we can see this in the driftless area. We can see it along our river banks as well. Next, we've got advection fog. So this forms due to moist air moving over a colder surface and the resulting cooling of the near surface air to below its dew point temperature. Advection fog occurs over both water and land. You can see here, this is actually kind of a form of advection fog. We have a marine layer pushing in here. Here's San Francisco and Oakland. You can see the same thing here. This is that marine layer pushing in. Marine layer forms kind of from this temperature inversion that caps and maintains and drives fog and cloud formation in the near surface area. One more picture here. This is the famous fog in San Francisco, and a very fun fact, it has its own name. This name came about in the early 2000s, if I remember correctly, from kind of a parody account that followed the Deepwater Horizon oil spill, the BP oil spill back in the early 2000s. Internet, well, won't say troll, but internet denizen came up with a parody account for the fog, and it was named Carl. So there's your fun fact about the San Francisco Bay fog and the marine layer that pushes in. It has its own name. The name is Carl. And here we can see some of the dominant fog types that roll in over the United States and North America. So many of these are forms of radiation fog. So here we can see kind of what drives it. Warm water coming in from the Pacific, meeting with colder water. We see this advection fog along the Pacific coast, radiation fog in the inland regions of the Great Basin, over in the Midwest as well, advection and radiation fog in the Deep South. One of the main ones that isn't a form of radiation fog or diabatic process is the upslope fog. Upslope fog is driven by adiabatic processes, which we will get into in our next video. And here we can see a map of annual mean number of days with heavy fog, so visibility reduced to below 1/4 mile. Right in Appalachia, we see some of the most intense, up in Maine as well, along the Gulf Coast, San Francisco Bay area, and kind of Big Sur region as well, and then up through Oregon, Northern California, Washington, up to Victoria and Vancouver area as well. So that's going to do it for this video, kind of talking about diabatic processes and the associated kind of cloud types or fog types, if you will, that form as a result of these diabatic processes. In the next video, we're going to be talking about adiabatic processes and walking through kind of how they function in general. So we will see you in the next video and start thinking again about kind of broader precipitation and cloud development. That's what these lectures are about. So we'll see you in the next one. Thanks.